but I just want to put this up one more time. So how does this, what's the idea here? Well, we've got some function f. Okay? We could write f of x. There's nothing wrong with writing f of x, but we just don't, we want to make sure we don't get this x right here confused with this x up here in the area function. Okay? So then we define a function, and I'm not showing you the graph of the function right now. What I'm showing you is how you would compute the output values for the function. Okay? So for example, if this area were 5, then what would g of, and here x, maybe when x is 3, what would g of 3 be? G of 3 would be 5. That's what I'm saying. That when you plug in a 3 for x, it outputs an area underneath the curve of 5. So this is this area function that we've been working with. Okay? So this is this g of x, which is this area function. Again, when you're having trouble, because there's a lot of symbols in that function, okay, when you're having trouble looking at it, first identify the variable. The variable is x, the upper limit of integration. So the way I think about this function is I think about taking that x point right there and sliding it back and forth. And as I slide that x value back and forth, the output is the area underneath the function, and that will be changing. So now here's the question, and this is the fundamental theorem of calculus. How does the area change as I slide x back and forth? It changes based upon what?
The shape of the graph.
The shape of the graph of f. Exactly. It changes based on the shape of f. So as I slide that x back and forth, okay, we're going to be adding or subtracting area, and that's going to be based on the shape of what? The function that we're finding the area underneath. Okay? So that's what the fundamental theorem of calculus says. So it says, given our area function right here, okay, then this function is continuous and differentiable. Once we've said it's differentiable, what is its derivative? How does g of x change? It changes by f of x. And let's prove the fundamental theorem of calculus. So that was a quick review of it, right? I mean, our goal is to show, we want to show that for g of x equal to a to x of f of t dt, what do we want to show? We want to show that g prime of x is equal to f of x. Well, what is g prime of x? Let's return all the way to the first unit, maybe the second unit of this course. Recall that g prime of x, or the derivative of any function, is what? It's the limit as h approaches 0 of the difference quotient. Right? So we're going to have to return all the way back to the difference quotient. Okay. So this is our goal. We need to do this to do the proof of the fundamental theorem. Before we do that, I want to say at least one other thing. I want to kind of prime us for this. Okay. So the next thing I want to say is let's just consider just some random function here. Let's call it k of x. And k of x, let's say, is defined on the interval from x to x plus h for a given h. For a given h. So pick an h value. It doesn't actually have to be positive, but if it's not positive, then I have to turn my picture around. But let's go ahead and just assume h is positive, but it doesn't have to be. If h were negative, then it would just go x plus h comma x. You would just invert this interval, right? But I need to have a direction here, so let's just do that. Okay, so consider k of x on this interval. Okay, then let's let x of h star be just some random point in that interval. Okay. Don't let your eyes glaze over with that notation. The star we usually use a star when it's just some random point inside of an interval. We usually put a star on it. The subscript h that I'm putting there is because I'm going to vary h. So as h changes, my choice of xh star will change. Okay. So here's my question to you. What is the limit as h goes to 0 of k of x h star. Because we're going to need this idea at the very end of our proof. So I want to get the idea out of the way first so you're comfortable with it. What do I see here? Well, I see that this piece right here, so this is my left endpoint of the interval, and it's fixed for some given x. And this is changing with h. As h goes to 0, what happens to this interval? The left side stays put, but the right side starts shrinking towards the left side, right? Do you see that? I feel like you'd start out with an interval like this, and this is going to stay put, but this is going to move in as h goes to 0, right? So as that happens, as h goes to 0, x of h star gets closer and closer to what?
X.
Yeah. If it's trapped, go to your Star Wars metaphor, if it's trapped in the trash compactor and the one wall of the trash compactor's closing in on it, where are you going to end up at? At the one wall, right? Same idea. As this endpoint gets closer and closer to here, my xh star, which is always between them, is going to just go to x. So that means that this limit right here, oops, is just going to be k of x. This is, of course, assuming, and I should have said this, for k a continuous function. This only works if the function is continuous, or it's only guaranteed to work if the function is continuous. Does that part make sense? Because that's going to be that's going to show up at the very end of our proof, and I'm going to say, therefore, we're done. Okay, I'll revisit this, but I mean that's what's going to happen at the end of our proof. We're going to need some argument like that. Okay. The next thing I want to do, I have one more thing to remind you of before we actually do the proof. We had this idea right here. If I have a function on a, b, and maybe here's my function, and it behaves, I don't know, maybe something like that, then this function has a max on this interval. Where is it? Maybe right here. Capital M. And it has a minimum on this interval. Maybe right here. Lowercase m. Okay? And we gave a nifty little theorem about a week and a half back where we said, well, little m times b minus a is going to be less than or equal to the area underneath the curve, which is going to be less than or equal to capital M times b minus a. Do you remember that theorem? Or that property? We went through that one about a week and a half ago. What's the picture, or what's the idea? I mean, we've got a lot of symbols up there. What are we thinking of for this property? What type of objects are we dealing with? How about this? I'm either, what's that?
A rectangle.
Rectangles, right? What is this right here? This is this rectangle. Let me shade this rectangle here. I'm going to erase it once I do it, but let me shade it for you. That's the area of that rectangle, right? It's got a height of what? It's got a height of m, and it's got a base of b minus a. So this right here is that black rectangle. Okay. I'll let you decide whether if you can fit that in there or not. I'm going to erase it just because now I want to do the same thing up here. What is this?
That's the area of the upper.
Yeah, that's this area right here, the area of that rectangle. And what do we know about the area underneath our curve?
It's
It's got to be somewhere in between the two, right? The smallest it could be is the area of the small rectangle. The biggest it could be is the area of the big rectangle. And it's essentially trapped in between the two of them. Okay? So don't forget that property, because that's